Okay, we ever take another integral. We've got the integral from 0 to pi, sine to the 5th x, cosine to the 6th x, dx. Okay, to get started with it, there's definitely a few different ways. You could probably do standard trig stuff to it, but I'm not that interested in that today. What I wanted to look at was Queen's principle, which tells us if we have an integral of some function f of x going from 0 to 2a, if we evaluate the function at f of 2a minus x, which is just the sum of the bounds, and if we get back f of x, then what that allows us to do is we can kind of just take the 2 off and write it as the integral from 0 to a. Same integral, just reducing the bound. Well, this works really nice in a case like what we have here. The 2a value is pi, and this is our f of x. So you can kind of just do this by looking at it because we know we have the supplementary angle formula. If our 2a plugged in is going to look something like pi minus x, supplementary angle formula on sine just gives back sine of x. Similar on cosine, but a minus sign pops out. The reason it's okay here, we're raised to an even power. If this was an odd power, it'd be a little bit different, but to an even power, the minus sign goes away and we just get back the same f of x we have right here. So that's going to allow me to use this formula. We can just reduce the bound to pi over 2 right away and bring a 2 out front here. And the reason for that is now it's set up to use the beta function on it. So we can go right to our formula. This allows us to do it without really doing any calculation at all. Well, I guess we have to calculate the beta function a little bit, but that's going to be pretty easy. What I'm going to do is, let's rewrite it though really quick. I need to get, for this version of the beta function, we need to set up the exponents. So for 5, I can rewrite that as 2 times 3 minus 1 just to set that up. And then same kind of thing on the 6. A little more complicated, we can write this as 2 times 7 halves minus 1. Just noticing that number is still 6 altogether. Doing it like this, our input on the beta function is just going to be this number here and here. So we'll go to our formula on it. This is going to become gamma of 3 times gamma of 7 halves. And then the denominator on it's going to be just the sum of these two values. Get a common denominator like 6 over 2, and this becomes gamma of 13 over 2. And now there's going to be a few different ways to reduce it. You could use the Legendre duplication formula, but I think I'm going to skip it here. I think what we'll do on everything is use this formula, take gamma of n, and it's going to be the same thing as n minus 1 factorial, or I guess a lot of times it's written as gamma n plus 1. Now typically you'd use this on an integer value, but we're going to kind of just do it even on these fractional values. So how it's going to look is, when I rewrite this, gamma 3 becomes 2 factorial, gamma 7 halves becomes 5 halves factorial, and this one becomes 11 halves factorial. But 2 factorial is just 2. What I'll do on this denominator is, let's expand it out. Again, a lot of times you don't do this if it's not an integer, but I'm just going to do it. So what we can do is still reduce this by 1, just like a factorial, and go 11 halves times 9 halves times 7 halves times 5 halves. We can keep going, but let's stop, because right here we get the cancellation with this one right here. And so to finish it, I just need to flip this fraction and multiply it all together. So we have 3 2's here. 2 cubed times 2 gives 2 to the 4th, or 16. 11 times 9 times 7 is going to be 693. And so for my final solution on this, we just get 16 over 693, and that's it. Okay, so there you go, quick and easy. If you did decide to use a formula on this here, you'd get a lot of the same kind of cancellation, because you'd have like a square root of pi term, those would cancel out. And you'd actually end up, after everything cancels, you'd end up with something that basically looks like this. So anyway, that's it for today. Thanks so much for watching. Have a good day.